Quantum mechanics has a reputation for being weird, and from all the strange and perplexing effects it exhibits, quantum entanglement stands out as being particularly intriguing. This is because it is the one phenomenon whose experimental results can make us question our understanding of locality or even reality itself. Now, entanglement is undeniably fascinating, but grasping what it actually is can be challenging. This is of course partly because it is indeed a highly counterintuitive concept, but another reason lies in how its unique properties are often explained. Most popular depictions of this effect rely on the direct use of what are known as Bell inequalities. Describing these inequalities requires considering a series of experiments on pairs of quantum objects measured at different angles, and then comparing the statistics of the observed results with what we would expect to see if the objects behaved according to the rules of classical physics. In other words, it is necessary to go over a good amount of math involving trigonometric functions and numerous probability calculations to reveal why entanglement is so special. So what I want to discuss in this video is my favorite and what I consider to be a more clear-cut way to explain how entanglement differs from anything else we experience in everyday life. To do this, we're going to rely on a game that involves a concept known as quantum pseudo-telepathy. I know this sounds like an unscientific term from the New Age quantum mysticism movement, but I assure you that everything we'll be covering here strictly adheres to the rules of quantum mechanics. As a matter of fact, what I'll be describing is a modified version of what is known as the Mermin-GHZ Game. So in the first part of this video, we'll explain how the game is played, and in the second part, we'll describe in detail how entanglement can be used by the players to win at this game of chance every single time. The game takes place in the not-so-distant future, and it involves a game host or referee called Eve. There are also 3 players, Alice, Bob, and Charlie, who need to collaborate to win the game. The players are isolated in 3 separate rooms and are not allowed to communicate with each other in any possible way. However, before the game starts, the players do have a chance to coordinate a common strategy. The rules of the game are simple. Each of the 3 rooms has a box with a push button and 2 lights, a red light and a blue light. In every round of the game, from her console, Eve turns on at random one of the 2 possible lights in each room. Then each player needs to make a decision based on the color of the light that turns on in their room. They can either push their button or not push their button. The players win a round of the game if the number of push buttons is even when all 3 lights were of the same color, or if the number of push buttons is odd when the lights were not all of the same color. So for example, if the blue lights were to turn on in every room and only Alice and Charlie push their button for a total of 2 pushes, which is an even number, they will win that round. Similarly, if none of them were to push their button, given a total of 0 pushes, they will also win since 0 is considered an even number. Now if instead only one of them, say Charlie, or all 3 of them had pushed their buttons, they would have lost because the total count would have been an odd number. Now, in the case where not all lights are of the same color, so when 2 red lights and 1 blue light turn on, then the players will win only if one of them or all 3 of them push their button to get an odd count. However, they will lose in all the cases where the push counts are even. So Eve has designed this game in a way that in every round, she picks at random one out of these 4 possible combinations of lights. She does this because she knows that even with the best possible strategy, there is still a 25% chance of losing every round. So after many rounds, say 100, the probability of winning the game will be extremely low. This is not very difficult to demonstrate. Consider the strategy where Alice, Bob, and Charlie decide that regardless of which light turns on, they will always push their button. This means that whenever any of the first 3 combinations of lights shows up, they always win because the lights are not all of the same color and the push count is odd. However, for the case in which all blue lights turn on, they will always lose. It is also easy to show that even if they change their strategy to, for example, push the buttons based in some other rule related to the color of the light that turns on, the probability of winning does not improve. This is also true if they try to adopt any type of randomized strategy. Of course, if you don't want to take my word for it, pause the video and see if you can come up with a better scheme. So, since the highest probability of winning a round of this game is 3 out of 4, or 75%, after playing, let's say, 100 rounds of the game, the probability of winning every single round is less than 1 in 3 trillion. Eve is then convinced that Alice, Bob, and Charlie will lose after just a few rounds. But to her surprise, after playing 20 straight rounds, they haven't lost a single time. The chances of this happening are quite low, so Eve starts getting very suspicious. She's convinced they must be cheating by communicating with each other. And since she doesn't see any wires coming out of the rooms, other than the ones that directly connect to her console, she decides to place electromagnetic shields or Faraday cages around each of the rooms to block any type of wireless communication. But even 50 rounds later, Alice, Bob, and Charlie still haven't lost a single round. So Eve starts thinking that they might be communicating in some unconventional way. Perhaps they are in possession of a modern device that distorts space-time and allows them to communicate via gravitational waves. Fortunately, Eve knows enough physics to understand that nothing travels faster than the speed of light, not even gravitational waves. So she decides to separate the rooms at a distance such as the time it would take the players to exchange information, even at the speed of light, is longer than the elapsed time between the moment their lights turn on and the instance they push their corresponding buttons. This will guarantee that there is no way they are communicating with each other to cheat in this game. However, after all 100 runs, to Eve's surprise, Alice, Bob, and Charlie managed to win every single round. So how did they accomplish this? Well, through quantum pseudo-telepathy, of course. Just as Eve suspected, Alice, Bob, and Charlie did have with them a special type of instrument, just not one capable of sending or receiving any type of information. Their devices were only pre-programmed before the game started. From the outside, these gadgets look extremely simple. All they have is a red button, a blue button, and a screen. In every round of the game, each player simply pushes the button that matches the color of whichever light turned on. Each device then displays on the screen a 1 or a 0 to respectively indicate the player if the button on their box should be pushed or not. Now, if you like, take a moment to see if you can come up with a way to implement an instrument that always provides the right number of 1s and 0s without communicating with each other. What you'll find is that there is simply no way to doing so using components that adhere to the laws of classical physics, like gears or switches or even state-of-the-art computers. Now, what actually powers these devices is quantum entanglement. So to figure out how they really work, we need to peek inside. What we find is a reservoir of particles, like electrons, one for every round of the game. And what's key here is that Alice, Bob, and Charlie pre-programmed these devices so that each triplet of particles is entangled. What this means is that these particles are correlated in a way that, regardless of how far apart they are from each other, making a change to one of them seems to have an immediate effect on the overall state that describes the combined system. So when all three players push their blue button, each individual particle is locally manipulated and probed by the instrument in a way that their combined response equates to an even number of ones on the screens. This, as we discussed, is precisely the number of pushes the players need to win a round of the game where all the lights turn blue. Similarly, if 2 red buttons and 1 blue button are pushed, the particles are manipulated such as the number of ones will be always odd, regardless of who was responsible for pushing blue or red. This gives the impression that the particles are interlinked and somehow know what the other particles are up to, no matter how far apart they are from each other. So entanglement between particles seems to endow Alice, Bob, and Charlie with some superpower not available through any classical means. Now, to really understand what's at play here, we need to talk about electrons and the quantum mechanical properties that can be exploited to enable this technology. Electrons have a property called spin, and the direction of spin is something we can measure. For example, we can design a device that when the spin of an electron is pointing up in the plus z direction, it displays a 0. Similarly, when the spin points down in the minus z direction, the device displays a 1. We can then assign a label to each of these two possible spins that corresponds to the measurement outcome and call them state 0 and state 1. The bar and angular symbols that surround the 0 and the 1 are common notation in quantum mechanics for what is known as a ket. But for the purposes of this video, we can think of them as markers for the two possible vertical directions the particle can take. Now, what's interesting about electron spin is that if we now have a particle with a spin pointing in the plus x direction and pass it through our measurement instrument, the resulting outcomes are probabilistic. Half of the time, the device displays a 0, and the other half of the time, it displays a 1. We then say that, in the context of this particular measurement device, the particle can be expressed as a superposition of being equally spin up and spin down. Mathematically, we describe this as a sum of each of the two spins pre-multiplied by a factor that, when squared, represents the probability of measuring each of the two possible outcomes, which, as we said, is 1/2. Similarly, for an electron with spin in the minus x direction, we also measure 0 or 1 with equal probability, which again we can describe as a superposition. But because the spin is pointing in the opposite direction, we associate a minus sign with one of the probability coefficients. That way, when they are squared, we still recover probabilities of 1/2 for each of the observed states. We can then think of this plus or minus signs as the direction in which the spin points along the x-axis. And for convenience, we can then assign labels to these two spins and call them state plus and state minus respectively. The next crucial point to highlight is that the orientation of electron spin is something we can modify. For example, if we have spin pointing up, we can use a magnetic field to rotate it and have it point along any other direction. A useful device to construct is one that takes a spin along the plus z direction and rotates it to point in the plus x direction and vice versa. The same device also rotates spin along the minus z direction to point in the minus x direction and back. We will label this transformation with an H to denote that this is what is known as a Hadamard operation, but this name is really not that important. All we need to remember is that this block takes spin in the vertical direction and rotates it to spin in the horizontal x direction, which, as we saw before, can be described as a superposition, and then can take the spin in the horizontal direction back to pointing along the vertical direction. Another important type of operation is one that rotates spin around the z-axis by 180 degrees. So when applied to spin in the plus x direction, this operation would then rotate it to point in the minus x direction. And if applied again, it would take us back to where we started. Mathematically, this is equivalent to multiplying one of the coefficients by a minus 1. And again, if applied twice, we recover the state we started with. The last operation we'll need is similar to the one before, except that instead of rotating by 180 degrees, it rotates by 90 degrees. So an electron with spin in the plus x direction will rotate to point in the plus y direction. And of course, if we were to apply this operation twice, this will be equivalent to rotating the x spin by 180 degrees, or again, multiplying one of the state coefficients by minus 1. But then an interesting question arises. If applying this operation twice multiplies by minus 1, what value do we need to multiply by when we only apply it once? Well, obviously, it would have to be a number that when it gets multiplied by itself, the result is minus 1. The only number that has this property is the imaginary number I. This means that an electron with spin in the plus y direction is also represented by an equal superposition, but where one of the coefficients is an imaginary number. This representation is still consistent with what we observe when we perform measurements, because taking the absolute value square of each coefficient still results in probabilities of 1/2. As we'll see in a moment, this will be the key ingredient to enable quantum pseudo-telepathy. However, for this to work, we will of course also need sets of entangled particles. To describe entanglement, let's start with pairs of electrons for which when we measure the spin along the z-axis, the outcomes are either 0 or 1, each with 50% probability, but the results are perfectly correlated, meaning that whatever outcome we see on the right, we get the same result on the left. These results on their own are obviously not evidence that these particles are entangled, since they could have simply been prepared independently to share the same initial spin. A way to test if this is the case is to include one of our rotation operations right before measuring their spin. This way, if the particles are independent and both pointing in the plus z direction, they will be rotated to point in the plus x direction. And as we saw before, the expectation is that we will see either 0 or 1 with equal probability for each particle, but the results of the two measurement devices should be completely uncorrelated, meaning that the results we see on the left are independent from what we see on the right. On the other hand, if we still see matching results even after individually rotating the spins, we say that these particles have a much stronger correlation and therefore it is very likely they are entangled. We can then express this as an equal superposition of both particles being either spin up or spin down, which is in line with the observations of simultaneously measuring 0 or 1 for both particles with probability of 1/2. We can also show that by using this mathematical representation, the observed results will still be perfectly correlated even when we rotate each particle. We just need to take this expression and replace each of the plus and minus labels with the corresponding superpositions of 0 and 1, and use the distributive law to show that the only terms that don't cancel out are the 0, 0 and 1, 1 terms, which then gives the same state we had before applying the H operations. Now, one of the strange features of entanglement is that when analyzed using standard quantum mechanics, it leads to known local effects. For instance, the math describes that if we were to measure only one of the two entangled particles, this will project the superposition state into one of the two possible outcomes, causing the spin of the second particle to instantaneously change to the same value that was measured, no matter how far apart the two particles are. It is then often said that the measurement of a quantum object is the one source of known local effects in quantum theory. However, there is another type of non-locality that is not usually discussed because it's a lot more subtle. Let's once again take our pair of entangled particles and apply a z operation, but just to one of them. As we previously discussed, this has the effect of multiplying by -1 one of the coefficients of our state. But because the particles are entangled, this causes an immediate change in the overall state that describes both of them, even if they're separated by a very large distance. In this particular setup, this known local effect is not perceivable because performing measurements will give the same correlated results we get even if we hadn't applied this operation. Rotating the spin of our particles before measurement will cause our results to differ. Instead of having correlated outcomes, they will now be anti-correlated. However, this on its own is not that exciting either because if we look at it closely, the change we're inducing is equivalent to locally flipping the output of one of the measurements. So even with this change, the known local effects induced by the z operation cannot be perceived. But now let's explore the case in which we have three entangled particles. Again, if we start with an equal superposition state, performing measurements will result in all of them being either 0 or 1. But notice that if each of the particles is rotated right before measurements take place, we can work through the math of replacing these pluses and minuses with the corresponding superpositions and show that the final state will now be one where there are 4 possible outcomes. What's interesting is that the results are now such that the total number of ones per possible outcome is always an even number, which, if you recall, is exactly what is needed to win a round of the GHZ game when all the lights are blue. So going back to Alice, Bob, and Charlie, what their devices are doing internally when they push the blue button is taking one of the pre-entangled particles in their internal reservoir and individually performing a measurement. The result they observe is probabilistic, but the parity is always even. Next, we need to find a way to modify the particles such as the sum of their outcomes is always an odd number, which, if you recall, is what Alice, Bob, and Charlie need when the lights were not all of the same color. This is surprisingly easy to accomplish using what we've discussed so far. If a z operation is first applied to any single particle to add a minus sign to the global superposition, the resulting state before measurement will now be one where the sum of all possible outcomes is always odd. Unlike the case in which we had two particles, here the change in sign induced by the z operation does result in an observable known local effect. The parity of the three measurement outcomes can be instantaneously changed by simply applying the z operation just to one of the particles, no matter how far apart they are from each other. This is something that cannot be done by any classical means. Unfortunately, this strategy will not help in the GHZ game because it will be unclear under which condition the z operation should be applied. Instead, if we replace the z operation with two s operations on separate particles, each of them will contribute a value of I to the prefactor, giving us I squared, which is equal to -1. So going back to the game, if S operations are applied when two players press the red button, it will be guaranteed that the players will obtain outcomes whose sum is always odd, allowing them to win when the lights are not all of the same color. So, to summarize, when all three players see a blue light and therefore push their blue button, particles are prepared and measured in a way that the parity of every possible outcome is even. On the other hand, if one of the players sees blue and the other two red, S operations are added when the red buttons are pushed to switch the parity of the outcomes to be odd. And in case it is not already entirely obvious, the reason this is called quantum pseudo-telepathy is because it gives the impression that the players of the game are telepathically communicating with each other to coordinate their outcomes. I find this to be wild. These results not only show that entanglement allows us to do things we can't accomplish with classical physics, but also that to explain these results, we need to rely on the use of imaginary numbers being applied to a global state in different locations but getting instantaneously combined to explain results that we see in the physical world. Now, carrying out the GHZ game in the exact same way we described it is virtually impossible with currently available technology. This is mainly because even though entangling the spin of several electrons can be done in practice, separating them by long enough distances while preserving their quantum properties for extended periods of time is extremely challenging. However, there are practical demonstrations of what we've described using photons. So this is not just a thought experiment, but something that has actually been demonstrated in practice. Furthermore, one can actually execute this experiment by mapping it into a quantum circuit and running it on a real quantum device. The results shown here are for circuits I personally run on an IBM quantum processing unit. As you can see, the rate of success per round is not quite 100% due to noise in the system, but is still significantly larger than the 75% that can actually be accomplished using only classical strategies. Finally, I want to highlight that the approach I've taken to explain the results of this experiment is the standard way of using quantum mechanics. However, there is an alternative but exactly equivalent method one can use to get rid of all the known local effects we've relied on to explain the observed outcomes. That being said, this does come at the price of having to accept that the multiverse interpretation of quantum mechanics is the right description of our universe, and that the players of the game must also be treated as quantum entities that can be placed in superpositions. Unfortunately, explaining in detail how all of this works will have to be the subject of another video.